Now let's move to the next part of our course is what is fundamentals of computer design. What we'll learn in this is we'll explore a simple processor design. We'll start it with a very basic processor so you understand what are the various parts of the processor, how to design a basic processor. Then we'll introduce the fundamentals of computer design, then outline the principles of instruction set designs, and we'll go into ARM v8 instruction set architecture. So let's get started. So for designing a simple processor, we will only need a few simple components, as in we are designing a very simple processor, so we'll start with very simple components. First will be memories. Memories are used for in terms of computer architecture, SoC processor to store either programs and data, or another way to say that is to store instructions and data. To keep things simple, we'll use a different memory for instructions and different memory for data. This is also the norm for real processors because we often want to access both instructions and data at the same time. So it's better to have separate memory for that to in order to access that parallelly at the same time. Then we'll also have another component known as register file. A register file is simply a small multi-ported memory. It's basically memory. It's slightly faster than accessing RAM, and which we'll talk about. So it's a register file is simply again a memory, but it's a smaller memory typically, and it's basically it can be accessed using multiple ports. By multiple ports, I mean you can read two addresses at the same time, or more than two, or you can write multiple addresses at the same time. Instructions will read their operands, what data to be read in, those kind of things from the register file. In our example, what we are going to do is our register file has two read ports and single write port. So that means we can write two values at the same time and we can read two values and write a single value in a clock cycle. Other things which we have is registers, some additional registers, ALU, which is the core of your processing machine, adders, multipliers, depending upon what functions you want to do or logical functions you want to do, for example, shift, XOR, etc. And then the output of that is result. Then we'll have decode and control logic. Each of the assembly level instruction will be converted into a specific operation to be done, and that is done by your decode and control logic. Control logic will be more like if you want to do a jump, if you want to do a loop, those kind of things are enabled by control logic. Now our processor, which we are going to design, the simple processor, can only load data from memory into our register file and store data from the register file into memory using special commands. Load, and these are known as load and store instructions. So basically, in our case, the processor, in case you want to read from memory, or in case you want to store in the memory, there are special instructions for that, which is known as at assembly level load and store. Architectures that restrict memory access to a few instructions like this are also known as load store architectures. Okay, so we cannot design a simple processor which will have memory, register files, ALU adders, logical operation functions, then there'll be decode and control logic. Our processor, which we are going to design, can load from memory into a register file and store data from register file to memory using special instructions known as load and store instructions. And this kind of architecture, as in which only allows writing to memory and reading from memory based upon special instructions, are also called load store architecture. Okay, so let's understand various parts of it. We little bit touched upon what are the various parts of it of a processor. We'll talk about little bit more detail. Registers. Okay, so registers or reg file are the smallest data holding elements that are built into the processor itself. So basically, you have processor CPU, and registers are kind of built into the processor itself. So it's kind of a memory, but it's a faster access memory because it's closer to CPU. Okay, and these are direct memory locations that are directly accessible by the processor. What can be in these registers is it may hold an instructions, it can also hold an address which you want to read, or sometimes it can hold directly data as well, or some other bit sequence as well, depending upon what operations your or your what instruction architecture set you have. So it can hold memory, it can hold data, it can hold addresses, but the thing is these are smallest data holding elements. It's closest to the processor and directly accessible by the processor. Instruction may specify like content of two registers to be multiplied together, and maybe then the output result may be put there. Okay, so those are registers. Some examples of that is program counter, as basically which reads what is the next instructions to be read, what instruction registers. You can have address, you can have accumulate register. Let's say you're doing some multiplication and you want to save some data at the output, you can have multiplication register. So the register is one kind of memory element. Okay. Then the other kind of memory element is which is known as memory. Now, memory is a hardware device used to store computer program, instructions, and data. Typically, memory has multi-layered architecture. There'll be processor, and as we saw, there'll be registers closest to the processor. Then you'll have a primary memory, also known as primary cache. Then you have secondary memory known as secondary cache. Then you'll have main memory, and you can have additional secondary memory as well. So memory is a layered architecture. That is memory that is internal to the processor is a primary memory, and typical RAM. It's called random access memory. So basically, you can access it randomly. And it's there is also called DRAM, which is dynamically accessible, and you kind of have to dynamically charge it. Okay, but this memory is external to the processor. Then the other memory can be secondary memories. These can be hard drives if you know in your PC. So memory basically can be categorized in terms of how close they are to the processor. One is register file, one is your primary cache. This can be RAM. Your main memory or secondary memory can be hard disks. Memory can also you can also categorize memory in terms of volatile or non-volatile memory. What is the meaning of that is a volatile memory is a memory that loses its content when the computer or hardware device loses power. So if the hardware device loses power, like the power goes away, then the content of memory is gone. Okay. And random access memory or RAM is an example of volatile memory. It's closest to the CPU after registers and primary cache, but it's basically once the power is gone, that data is lost. Non-volatile memory is the memory if which it keeps content even if power gets lost. Your hard disk can be those memory. Your EPROM is also an example of non-volatile memory. So basically, these are memories that keep its content even if the power gets lost. So memory is basically device used to store data, programs, instructions. And memory can be hierarchically understood in terms of how close they are to the processor, or also basically you can classify them into types of memory as well. Some high level differences between register and memory. Register holds operands, instructions that CPU is currently processing. Right now, what CPU is processing that should be closest to the CPU, and those are stored in the registers. Memory also hold instructions, data, and the program, but basically it may not be right now which your CPU is gonna use, but it's something which is gonna access. Maybe it's a big program, so you'll be converting that into instructions, and that will be loaded from a memory. But register file will contain what is CPU currently processing. Registers hold small amount of data around, maybe depending upon what kind of architecture it is. It can be 32-bit, it can be 64-bit, depending on what kind of architecture it is. Memory, on the other hand, on the computer or on an SoC can range from some gigabytes to terabytes. So it can hold large amount of data. CPU can operate on register contents at the rate of more than one operation in one clock cycle. So CPU access to registers, working on the reg file, CPU can do it very, very fast because it's very close to CPU and it's directly accessible. So you can access the register content at sometimes at a rate of much more than one clock cycle, whereas CPU access to memory is slower than access to a register. Some typical examples of registers are your program register, accumulator registers, instruction registers, address registers, etc. Type of memories are RAM, DRAM, SRAM, DRAM, your EPROM, etc. Registers can be controlled, like registers can control the flow of the program. Like if your program has if loop, else loop, more in assembly like jump, loops, registers can control and basically store the information, and registers will have control information as always. Memory is usually not control based type of logic. Registers are faster than memory, and RAM is much slower than register in terms of access, both how you can access and how long it takes to get the data out. Okay. So now let's go into basically designing a simple 32-bit processor. And it's going to do simple instructions, but we'll do it step by step. So we'll assume all our instructions are encoded in 32 bits. So basically, whatever instructions we are going to give to the CPU, whether you want to do add, you want to do subtract, multiply, which two operands you want to do, basically all our instructions are coded in 32 bits. Our registers data path are also 32 bits. So basically what this means is you are telling CPU, let's say do multiply, but on what data you are multiplying, let's say A1 and A2 you are multiplying, those are also 32 bits. So that means our registers and data path are also 32 bits. Your memory is accessed with 32-bit address and returns 32-bit data on which we operate. And our processor, the processor, as we said, has a register file that also has 32 registers, each 32-bit. And so basically, in order to access this, basically we need 5 bits because 2 raised to power 5 is 32. So basically, in order to address our rec file, we need 5 bits. Okay. As in our data path in this case can be 64-bit wide, as in because the data path size and the instruction size need encoding size need not be same. But basically our data, if you want, in our case, this case, our data path can be 64-bit wide also, and that does not mean we would need to change the width of our instructions. The instructions can still be encoded in 32 bits. Okay. So this just to avoid the confusion, since we are using everything as 32 bits, just to make sure, as in our data path for this can be still be 64 bits, while our instructions are encoded in 32 bits only. So this is our processor. Our instructions are coded in 32 bits. So we have registers and data path also encoded 32-bit wide. Memory is accessed with a 32-bit address and returns a 32-bit data. We have a register file which basically has 32 registers, so we can access it using 5 bits. Now, typically, right, in an assembly program or in directly CPU code, which is basically going to do some instructions, they're typically set of instructions. We are gonna go into a little bit more details as we go forward, but think just to give a brief overview, typically operations which can be done inside on a CPU or ALU is are basically can be written in form of what is known as set basic instruction set. And these little bit detail will go into a little bit later in terms of instruction set architecture, but let's understand what kind of basic instructions can be. The instructions can be maybe add two operators and put the result somewhere, and subtract, or as we saw, right, in our case of load store architecture, basically load from memory, store into the memory, move from one location to another. Or there can be control structures like jump, loop, return, those kind of structure. So basically, these are some basic set of instructions which are can be coded in assembly language. Of course, depending upon processor to processor, these commands will change. These or what operations it can support. Maybe some directly support multiply, some don't support multiply. Those kind of things can also change depending upon what you are basically ISA or instruction set architecture is. Now, for example, let's say a CPU, or you as you have, let's say you have a C level code which does this operation x equal to y multiplied by y plus z. And let's assume x, y, z are stored in memory location 0, 1, and 2. So a typical assembly language code can be like move. Basically, this is what is showing is move whatever is on address 1, move it to A. Whatever is in address 2, move it to B. Then basically you are doing this add A and B, okay, and then store, and then multiply A and B, and whatever the results is, move to a particular location. Okay, so this basically normal code. Don't try to go into detail of this code, but basically any normal code C level code will convert it into this assembly code, and that assembly code is what your CPU is gonna execute, or your computer architecture system is gonna execute. And this is basic set of instructions for those, and this is what we are gonna design, that once you see these set of instructions, how is CPU gonna perform those instructions, or design at a at an RTL level or at a microarchitecture level, what this how these operations are going to take place. Okay, one another concept which is important is, and just I will briefly touch it, is what is known as code density. Code density loosely refers to basically how many microprocessor instructions it takes to perform a requested action, and how much space these instructions take up. Generally speaking, the less space an instruction takes and more work is done per instructions by a microprocessor, the more dense the code is. So basically, if per instructions it takes lesser space and more work a microprocessor can do, then code is known as dense. Typically, dense code have lower power requirement, so it's basically there's a lot of work which is done to make code dense, but that requires you to improve your instruction set architecture and also the compiler, and which we'll briefly touch upon. So for example, let's say you want to do a memory copy, which basically from particular set of addresses you want to copy, from a particular set of source addresses you want to copy to a particular set of destination. So this would be your C code, as in you have source, you have destination, and basically you will keep doing this source to destination, and then keep doing that. Now let's say if your instruction set architecture is simple, you will basically write this in a larger set of commands, which basically your instruction architecture supports. So usually you'll move the data, you will add the data, and there's some operation you will see whether count is zero or not. If count is zero, you will end the loop. So you can see, without going into too much detail, you have to do a lot of instructions here. If I count here, 1 2 3 4 5 6, around 6 instructions are there. And so basically you have to do 6 instructions. Now let's say if uh, your processor supports multiple complex instructions as well, which is the case of, let's say ARM processor. This may be a simple, let's say MIPS processor. Then basically you will have loop, do something, and basically these are complex instructions. Not only this can do plus, this can also then store, okay, or subtract. Okay, so these you can see is done within the loop in 2 instructions. So basically you are able to do the same job with less number of instructions, and you are also taking less space, and more work is done per instructions. So this code is more dense. Denser code is important for power saving processor. Denser code allows you to save power because then you are accessing lesser and basically it's doing more per instruction. And but just just because in this case, because your processor supports complex instructions, th- it's able to do that. But basically tensor code can be a function of not only your processor able to do complex instructions and basically your efficient instruction set architecture, but it is also a function of underlying compiler engine. Okay, for example, let's say you have your C code, and if your compiler is not good, it can still convert that this code into this, even though architecture support this, instruction set architecture support this. So your compiler also plays an important role when you have a dense code. So both compiler and what instruction set architecture which exists, both play a good role in having your better code density, and is an important goal for power saving processors. So we briefly touched on it. We'll come to back to it a little bit in more detail. Now let's start designing a simple processor. First, we'll basically think of an instruction, and we saw some examples of an instruction. A simple data processing instruction in our processor can be simple. Okay, simple like this: what instruction you want to do, add, move, subtract, which we saw. Then basically destination, source, and second operand. Okay, now your second operand can be another, or maybe data something which is in memory. Maybe let's say you are doing x plus plus, and then basically your second operand can be just what is there in the memory, or your second, or you're doing x plus y, then the second operand comes from either immediate value or maybe a register. Now, given this, our we have 32 bits to encode our instructions. So these are our instructions, sample format of our instructions, and we have 32 bits to encode our instructions. There are two simple instruction encoding formats which we can design. Okay, one format is basically this: some bit you give to operand, what operation you want to do. Then this is the address of your result. Then this is address of one operand, and this is address of another operand. If you remember, we had our basically instruction register file which is 32 depth. So basically we are keeping 5 bit each for storing address of one result, address of your operand one, address of your operand two, and then you have function. So sometimes if let's say opcode is same, opcode decides, which is this, what operation you are going to do. Sometimes if opcode can be same, then additional information is given there in the function to basically do that operation. This is the case when basically two operands are different. If it's an immediate, we can basically have opcode result one operand, and then the second operand is in memory. Okay, please note this is 16-bit. Since our data size is 32-bit, this is only 16-bit. We can only do certain set of operations, plus as in we have to make sure as in this data is converted to 32-bit when the operations are done. So which we'll also design for. So this is when you're doing something immediately in the memory, but the data you can store immediately in our instruction set is just 16-bit. So that limits some things, and also you have to take care that it's converted to 32 bits when you're doing the operations. Okay, so these are two ways we can encode our instructions. Encoding is nothing but basically you're saying, okay, maybe for adding my code is 00, and let's say add on address 0, then the other address is 1, and store in address 2. So this is basically just giving information to the CPU that you read from this address one operand, you read from another address this operand, and then add it because operation is add. So don't get confused about it. This is very basic. So basically, this is how you can create an instruction set, which basically this will convert into this code and which will go to CPU. So let's basically design this part of it a little bit later. Let us now look at encoding the instructions. So we talked about opcode, and this is one way of encoding basically your instructions. And this is another way. Here, rather than basically the second operator, you and function, you have something called immediate. Immediate is something simply a numeric value stored in the instructions itself. Yes, okay, basically it can be result of a previous calculation or something you want to do. One thing to note again here is basically this immediate is 16-bit, not our normal 32-bit, and how that has to be handled, what kind of limitations it causes, we'll come to it little bit later. So basically, this slide describes the encoding of instructions stored in the memory. There are two types of instructions which we can think of. Of course, as in a normal, more complex processor, there will be more, but we are right now trying to design a simple processor. And we are also assuming a simple fixed length instruction. What is the meaning of that? Is all our instructions are 32-bit. Okay, and basically that is basically how it is adopted in most what is known as reduced instruction set computers or RISC processor. In there are more complex instruction set known as complex instruction set computer. There the machines will have more complex and even variable length instruction encoding scheme, and these variable lengths, as we talked about, a concept known as code density allows you to have more code density and maybe lower performance and better, basically lower power and better performance as well. So basically these are various ways to code the instructions. Okay. Now let's go a little bit more detail about this. Let's say the op bit actually tells what, or it's a short for what is known as opcode, and it's going to tell what operation you're going to perform. Okay, so you can do maybe additional operation. Let's say your assembly code is add, and let's say code for add is 0, or let's say your assembly code is, and let's say code for add is 0, and then, so basically this will then contain 0, and which will then mean that add is being done. Now it can also happen that say opcode for all logical operations, let's say, is 1. Okay, so basically then the logical operation here you will fill is 1, and of course this is your 6-bit. Now now basically sometimes if opcode is same, let's say logical operation can be and that you support maybe NAND, just example, let's say XOR, right? Now this function, the function here will then tell you what actually operation has to be done. So if the opcode have this have the same for instruction that have the same opcode, the function will give us additional information about operation to be performed. For example, let's say opcode for logic, let's say it's 1, and which logic operation has to be done and XOR, that will be given by a function. Okay. And immediate is something which we talked about, where basically you are doing rather than two operands. Okay, you only have one result, one operand, and other operand is stored in the memory. This can be result of previously done addition, something like this kind of operator as well. Now let's start designing it. So we talked about instruction. Now let's basically start designing and go to a little bit more lower abstraction level and start designing it. Okay, so now we'll first design the processor data path. What is the processor data path is? It will have what is known as program counter and your memory. A program counter basically stores, what does it store? It stores the address of the instruction. Okay, so basically it stores the address of the instruction currently being fetched from the memory. So basically program counter basically will have address here this, which will be fetching from the memory what instruction is being should be performed. Okay, so basically it will give address to the memory and your instruction will come out. Now once that is done, basically you will increase the address by 4, which this is 4 bytes, which is basically 32 bit. So basically you will go to next program counter value, next address value for our memory, as we said, right? It's basically next byte will be basically after 4 byte next address, as memory is storing 32. Okay, so basically next address will be plus 4, which is 32 bit. So basically simple data path increases the program counter by 4 bytes on each cycle and allows us to each 32-bit instruction. Okay, so each this is 4 bytes. So you'll read this instruction. Then to read this instruction, you have to increase address count by 4, 4, basically 8, 8, 16, 30, 24, 32, which is 4 bytes. 1, 2, 3, 4. So you'll increase it by 4 byte here to go to next instruction. Then of course this is just the program counter access, as in you will still need to do computation and those things. So we just will be building it small by small, block by block. So now we have built what is a basically program counter and instruction memory. A program counter stores the address of the instruction which has to be read, and will read that instruction by memory, and then it will increase the program count by basically what is our instruction size, which is 4 bytes, which is 32 bit. It will increase by that. So now we have designed the program counter part of it. Now we'll add something known as a mux to allow jump. Okay, so you might have seen, right, in your assembly code, there is a jump. Okay, right now what is happening is, in the previous case, your address is always increasing by 32 bits or 4 bytes. Okay, so basically you will have some assembly code, let's say instruction 1, instruction 2, instruction 3. This is stored in the memory. Let's say this like this: instruction 1, instruction 2, instruction 3. So this is, let's say, stored here at this address. For 0, 1, it's our each of our instruction is 4 byte. So this is 0, 1, 2, 3. This is 4. This stored at 4th byte. 4, 5, 6, 7. This is stored at 8 byte. Okay. Now this is our assembly code being executed. But sometimes there are jump statements. So jump may ask us to jump to a particular address. Let's say this address to be jumped to is 28. So basically it will be something like jump to 28 address. Here, basically by default, your code execution would be that you will execute this code, increase it by 4 bytes, execute this code, increase it by 4 bytes, execute this code. But then after that, you will jump to an address 28. This is the code. Now, how do you do that? How do you make jump in the hardware? Basically, for jump, you will add a mux here. Okay. Normally, your program counter increases by 4 plus 4. But here, other input will this of the mux. So basically, if it is jump, which is true, equal true, you will feed another address, and the program counter will directly go to that address. In this example, that address in our case would be 28. So it will directly feed 28. Program counter will load 28, and you will directly go to an address 28 to read this. So this is basically a mux added to allow for jump or branch operation. Branch can be if and else also. For example, let's say we have if statement. If it is not true, then basically you have to go to else. That is kind of can be implemented as a jump directly to this address on else. So basically this can be used to implement jump or branching of basically processor instructions. So we started with program counter, we added memory, now we added support for what is known as jump or branch statements. Now let's continue building on this simple processor. Now basically now we want basically the processor to execute certain operations. Okay, so we need to execute this operation. We will add what is known as arithmetic and logic unit. Okay, so arithmetic and logic unit can basically do it. If you, as we're not going into details of inside of ALU, basically you can do add operation, basically whatever XOR operations and other addition, subtraction, all multiplication, whatever operations you want to do. So it's a simple arithmetic logic unit. It can be coded in simple Verilog like a case statement based upon X, and then this is covered in our basic Verilog code. Okay, so basically now we will do what is known as a simple execute of logical operation. Okay, so basically you had address, instruction came out of it. Okay, so instruction, as we said, will look like something like this: a 32-bit opcode function, your operator's address. Okay, and our register file is basically 32-bit, so each of these addresses will be 5-bit. Okay, now for processor to execute this, let's say you have this, let's say operators, this is rs1, rs2, this is result. All this is basically your program counter or memory is giving this output. Okay, now what is the meaning of this has to be decoded. That what is the meaning of opcode? Basically opcode, what is the mean, what are the elements on which you have to perform these operations, again has to be decoded. So that's why there is something known as instruction decode. Decode in this simplistic case is nothing but maybe identifying what are the individual addresses of operand 1, operand 2, and basically result where you have to save the result. So this then basically are addresses. So let's say this is, let's say you want, what you want to do is you want to on address 0, on address 4, and let's say address, and let's say 28. You want to on do an addition of what is value present in address 0, what is the value present on address 4, and save it on address 28. So your opcode, let's say for addition opcode is 0, and then basically address 0, address 4, and address 28. And let's say function for that is also 0 when you want to do addition. Now you're basically outside of memory, your instruction will look like this. Okay, now this instruction has to be broken down. So basically you have to tell to the register, you have which address has to be read from the register file will be 0 for first operator, okay, 4th for second operator, and 28 for result. So basically this full 32-bit registers is broken down into these aspects, and this is known as decoding in a simplistic case. In a complex processor, the decoding may involve multiple more elements. So this then goes into register file. Register file then gives output. Basically these data outputs are provided, okay, which is basically value which is stored in address 4. So let's say this is 1, this is 2, so 1 will come out here, 2 will come out here, and then basically this function is determining, and opcode is determining what function is being done, and this in case is addition. So output result will be 3. Now this 3 will then be basically given back to the register file and stored at a particular address, okay, which is given here. Read address is given here. So at address 28, value 3, which is output of the addition, will be stored. So this is how basically your program counter, and then basically your ALU function, which first decodes the instruction, accesses the basically value of the instruction data from the register file, and that's why register file is closest to CPU. It's faster to access in one cycle. Then performs an ALU operation and then gives it back to the address where it has to be saved. And the address was also again part of the instruction which was provided to the CPU. So we added a register file and ALU to it. So we started with processor data path, which is program counter. Then we added a register file and ALU. Okay, so we're slowly building up our simple processor now. So we have added register file and ALU. Let's, as in we covered this part already. So we added program counter. Program counter can read from the memory. Then there will be an instruction. Then instruction will be decoded. decoded, function will also be there, and basically then ALU operation will happen. Now, basically, we another thing which can happen is loading from data memory. Okay, what is that? Is result of is going to be coming from a data memory. We can extend data path so that we can implement the instruction that loads from data memory. Okay, so now you can load instruction from the register, or you can load instruction from the data memory, as basically load from the data memory as well, which is the instruction. So a instruction can either be loaded from program counter, or your instruction can result, basically data memory can a result can be from data memory as well. Okay, so there is this instruction decode. Now instruction decode result from should come from ALU, or it can come from a memory. Sometimes you directly want to access a memory, and memory address gives the result. Maybe you're reading a memory, and maybe you're doing address addition and you want to read from a memory. There the result can also come from the memory, and this will be decided by your instruction code. So basically you're giving instruction that result has to be read either from memory or ALU. If it is from memory, okay, then you will read it from memory, and this will give an address from where it has to be read, and then basically it can be stored in the register file. Okay. And an example of this will be, for example, let's say you want to add basically your address from which you want to read from memory can be sum of two addresses. So let's say A plus B address, you want to read data from that memory, and that you want to store in the register file. So basically here your one operand will be A, will be B, and basically here read. So this will give you address, and this will be the address where you want to store this output in the register file. This will give you an address. This address will go to data memory. Output of that will be the value stored on this address, and that basically then will come to register file as that address. So that's where you want to use the result to access data from a memory. So again, this basically you could have done it in multiple steps as well. You could have done first do the addition, then save that data somewhere, then access the memory and get it. What this has enabled is this has created this compound instruction. So basically code has become dense because this can also be done like first you do ALU operation addition, store that in a, let's say, program counter, then you kind of do a load instruction and load that from a memory. So this would have been like four commands or four assembly commands, which can now be just made one command because of this adding data memory layer directly here. So this can make the code dense. So this we added even in our simple process. You can also store to the data memory, right? You can not only read, okay, you can also store to the data memory. So storing to memory requires that we both provide an address and data to write. So basically you provide an address, okay, and basically what data you need to provide, and you can store it to the memory as well. And again, we added this logic, you can read from the memory as well. In addition to that, you can have, which we saw right in our opcode, that you can basically want to do immediate operation, which is immediate is basically rather than loading one operand from basically your register file, one of the operand is directly part of the instruction. So how do you do that? Basically this is what we have seen, right? So you have opcode, result address, first operand, and second operand is part of the instruction code itself, and that is what you want to use in the operation. And we had said, right, you had to notice this was 15-bit, this was 16-bit, and our normal operation is 32-bit. So in order to use it, you have to kind of sign extend this immediate value. So basically here you're selecting whether you are reading from immediate or register file. So if you're reading from register file, the data will come like this. But if you're using from immediate, the data will directly come from your instruction code, decode. So you can choose, and that will go into your ALU operation. But before we can do that, our immediate values are contained with basically so that instructions will be less than 32-bit. So before we can use these values within our data path, we have to increase their width to 32 bits. This must be done by preserving numbers sign and value. Okay, so we need to do sign extension. If you remember for college basics, there is two complement form. So we'll simply duplicate the most significant bit to do a sign extension. If most significant bit is 0, we will just duplicate with 0. If most significant bit is 1, we will duplicate with 1. And now, so we have added support for immediate instruction also. We have added support from directly writing into the memory or reading from the memory, and basically move forward in designing our simple processor. Now we can also support branch. Okay, branch instruction, which is basically branch instruction is nothing but similar to jump, that you want to just go to the next instruction. Okay, rather than basically load from program counter. We had said we'll do our branch instruction where basically you are jumping to a particular value, and here we're just, how do you jump is basically you, our instructions now start like, basically they are separated by 32 bits. So you can simply multiply by 4. Our target branch address is computed relative to the program counter. Okay, so if you shift left by 2, right, or multiply by 4, as all instructions are 32 bits, so shift left by 2 kind of is basically going to next instruction, which is same as basically multiplying by 4. You can go to our next instruction and branch it, jump to the next level. So we'll jump to the next instruction level by multiplying by 4, and this can be enabled basically like this. Your program counter, if you want to branch your program counter rather than addition of 4, okay, you basically multiply by 4, which is this 2 left shift operator, and which is you provide here. So now you can basically go to the next instruction or jump. We are fixing a fixed jump here, so you can multiply by 4, and that gives us a fixed jump where you can increase your program counter. So this is how you can also do branch or jump kind of instruction by, we had earlier just added a mux here. Now we have connected this mux to a multiply by 2 operator, and then do this branch operation. So let me now show you one of the examples, basically where it shows on a real ARM processor how the visualization of when this all operation, multiple loading of data, assembling of data, doing ALU operation, all that is happening. Let's and you look at it from a visual angle. And in addition to that, there is a link here to basically show to implement a simple processor example. So please implement this on EDA Playground and then submit your assignments. And let me just unshare and share again to show you the visualization of a real ARM processor, how it performs this ALU operation. So this is the ARM processor. You can see here, there is some stuff here, basically your multiple registers. Okay, it must have program counter value and other values. And you can see, right, as in these are program counter values where the values are picked up. And let us play to see how this operation changes. Okay, you can see, right, your program counter is increasing here. Okay, and multiple operations, based upon that multiple operation, data is picked up from different locations. certain operations are performed on that. And this is, you can this is very interesting. You can zoom in and see how each of the individual operations are happening, what lines are turning on. So this is a pure schematic of your ARM processor. Okay. So next, we'll go into more detailed about your processor. We have designed a simple processor. Now, what we'll do is we'll go into fundamentals of computer design, and let's start with that. So far, we have understood at a basic level what is computer architecture. We went through introduction of computer architecture. We understood how over the years performance of processors and computer architecture system SoCs have improved. Now, and we also designed our very simple processor. We understood various aspects of it, program counter, register file, and other aspects of it. Now we'll start going into more details, but we'll again start with basic fundamentals of computer design. Okay, so the fundamentals of computer design, it's very useful to remember that when we're designing a processor, we must make the design choices to understand the constraints at many different levels. We have understood, right? There are basically various parts of this which are involved. There is various abstraction level like architecture, microarchitecture, and we must understand each of those levels at a reasonable level to make correct design choices, or a computer for a computer architect to make correct design choices. He should understand the constraints at many different levels. The design process is very complex and it involves many interrelated trade-offs. Basically, simply, we cannot just start designing by instruction set in isolation. We have to think about what is a market we are trying to address, what is the performance goals we have. So basically, a lot of constraints computer architect has to keep in mind to design a computer architecture. So let's start with, again, going back into a little bit more detail about what are the various abstraction level. One is architecture. It's basically, think of this as it's also relatively used with what is called an instruction set architecture. What are the instruction sets we are going to support? So it's a set of specification allows developer to write software and firmware. Okay, and this includes the instruction set. So think of this as a bridge between software and hardware is the architecture, your instruction set architecture, what instruction sets you're going to support. This defines the instruction sets, sometimes exceptions, memory models that basically person or the team who is writing software or firmware has to rely upon. Okay, or the team working at the operating system level. It also includes the definition of system registers, debug and trace architectures, and maybe details of virtual memory system as well. The terms, as I said, right, architecture and instruction set architecture, or in the short form known as ISA, are both used interchangeably, as in one is used in place of another as well. And what we are actually defining here is the hardware software interface. It's the interface between hardware and software, which allows people to write your software, compiler. So basically, you have a set of C code, and basically, if the compiler has understanding of instruction set architecture, it can convert that into assembly code. And to convert that into instruction set, it has to know this. So computer architecture, right? If you design a system, it has application, algorithms, programming language, and then your OS. This is where computer architecture set. Okay, your basically instruction set architecture. That is your higher abstraction level. It's an interface between software or OS to the hardware. Then there is microarchitecture. We'll talk about what is microarchitecture. Then there is register transfer level. This is basically the real hardware description, RTL description also known as, and it's where the implementation details come into the picture. Then this goes more into the VLSI design in terms of what are the gates which are there, circuits which are there, devices, what technology you're using, maybe physics effect, electromigration effect. So, but this is where this course lies. And basically we starting with instruction set architecture, or also known as architecture, where basically it's an interface between your OS or software and your hardware level. Now the lower level abstraction level is microarchitecture. Okay, so basically we said architecture is an interface between basically software or OS and your hardware, and it's defines an instruction set architecture. Microarchitecture is a specific implementation of the architecture. It's one specific implementation of the architecture, where basically even though you can have two processors or two computer systems with the same instruction set architecture, but they may have different implementation of that architecture. And it's basically a logical organization or inner structure of the computer. What kind of cache it is have, what kind of memory it is have, what kind of virtualization it can have, what kind of program registers it can have. Those are details of microarchitecture. Now think of it this way, an easy way to understand microarchitecture. You have two cars. Okay, so basically both cars can take you from place A to place A B. So that means as in car, the instruction set or the architecture of the car is same. Both allow you to take from one place to another. But one can be a sports car, one can be a just general purpose car. Okay, so the cars, how internally they are built, how at the detail level what their individual things are, they are the same. But the driver who's driving the car is has a steering and has a stick shift or a gear. So basically instruction sets which the driver is going to use is the same, but internal details can be different, and that is a micro architecture level. Okay, so you can have two processors implementing the same instruction set, but with very different microarchitecture. Basically, they are built very different ways, similar to what, like you can have two cars and they both have steering and stick shift or a gear and an accelerator and a brake and a clutch, but they can be implemented very differently. One can be a sports car, one can be just a normal car. Different microarchitectures may aim to make different trade-offs. Like even though instruction set architecture is same, there is can be for that the implementation of that particular instruction set may try to focus on performance more, or maybe cost more, or maybe power more. Okay, so basically you can have two same instruction set architectures or two same architecture, but one microarchitecture is focusing on performance, another microarchitecture may be focusing on low power, or maybe another microarchitecture can be focusing on cost, or maybe a multitude of those, right? So you can have same instruction set but being implemented differently at the microarchitecture level. Okay. So architecture is what is simply basically colloquially also known as instruction set architectures. So it's something which is visible to programmer. What is memory? What are the registers? What are the operations you support? You support add, you support subtract, you support multiplication. Maybe you directly support loading from memory or saving into memory. All those basically operations that which are part of instruction set architecture, you define them. And also what are the execution semantics, what are the interrupts you support, what are the input and output you support, what are the data type, what is your size of instruction set, what are the data types. That is something which is part of your architecture definition, or how architecture is defined. Then microarchitectures basically is trade-off on how to implement a particular instruction set architecture. The trade-offs can be between speed or performance, how much power, cost, these kind of things. For example, like same instruction set architecture may have different pipeline depth, maybe different number of pipelines, memory, cache size, silicon area, peak power, order of execution, different bus widths, different ALU widths, all those can happen within the same set of for the same architecture, for the same instruction set architecture. And basically, you are designing microarchitectures to take care of these speed, energy, and cost trade-offs. This is an example of you have same architecture or same ISA, but different microarchitecture. Okay, so one is AMD Phenom X4, another is Intel Atom. They have the same architecture. So basically, both are supporting x86 instruction set, but one is quad core, so your microarchitecture is different. One is single core, so they are one is optimizing on the performance. One is 125 watt, and other is just 2 watt. So basically, you are one is optimizing on the power as well, another is not. You can have decode three instruction per cycle per core, and decode two instruction per cycle per core. And basically, different L1 cache, different same size L2 core cache. One is out of order, another is in order, different frequency, but they have the same architecture. Okay, so your instruction set or instruction set architecture or ISA is both are supporting x86, but both are trying to cater to different markets. Both are focusing on different aspects of the performance. So micro architecture is different. So one is from AMD, another is from Intel, one is Phenom X4, another is Intel Atom. Okay, and of course, right, different architectures can have different microarchitecture. So you have different architecture. They're supporting again AMD Phenom X4, IBM Power 7. AMD Phenom X4, as we saw, is supporting x86 instruction set. So your architecture is x86 instruction set, while IBM is supporting power instruction set. So their architecture is different, and even their microarchitecture is different, which is like uh, obvious, right? As in different architectures can have different microarchitectures. So you have quad core here, 8 core here, different power requirements, different frequency, different L1 cache, and other memory elements. So basically, architecture defines your instruction set, and for the same architecture, you can have different microarchitectures and lower level details, memory, cache components, and different microarchitectures are designed to take care different goals or market goals, performance goals, speed goals, cost goals, etc. Now, at a further lower abstraction level is what is comes as hardware or implementation. This is the realization of the physical structure of the design, how the logic in the design is, what technology you are going to use. Maybe you're going to use 90 nanometer, maybe you're going to use 4 nanometer. So what is the technology you're using? How you are packaging your chip. So these are more physical details at a much lower abstraction level. You can select parameters for a given microarchitecture. For a given microarchitecture, again, you can implement differently. You can, for the same microarchitecture, you can implement using 65 nanometer technology, 20 nanometer technology, or a 7 nanometer technology. So technology for given for the same microarchitecture. Okay, different micro architecture, same architecture, but you can implement for different clock frequencies. Like one is working for 1 gigahertz or 2 gigahertz. So even for the same microarchitecture, logical or hardware implementation details can be different, and that is what is known as hardware or implementation level abstraction level. So one of the important aspect for us in architecture design is performance. Okay, now for performance, we also need to understand there is an important law which is used to understand what is the impact of a particular change or impact of multiple changes at architecture level is going to impact performance, and that law is Amdahl's law. So to, to understand it generally, suppose let us say, okay, Moni has to attend an invitation. Okay, Moni's another two friends, Dia and Hina, are also invited, but there is a condition that all three friends have to go separately, and then all of them have to be present at the door to get into the party, to get into the hall. Now, Moni is coming by car, Dia is coming by bus, and Hina is coming by foot. Now, so basically, all three have to be reached together to get into the party, but they're using different means of transport. So they basically different have different individual speed or performance. Moni is coming by car, Dia is coming by bus, and Hina is coming by foot. Now, how fast Moni and Dia can reach there does not matter. because they have to wait for Hina, and that she's the slowest, so they have to wait for Hina. So to speed up the overall processor, one, we need to concentrate on the performance of Hina other than Moni or Dia. And this is what Amdahl's law indicates. It relates the improvement of system performance, which is in our case basically Hina. So it relates, okay, Hina, how fast can Hina go? Okay, she's coming by foot, so she's the slowest. How fast she can go, and then depending upon how fast she goes, how it impacts the overall reaching time or overall performance. Similar, so Amdahl's law also kind of relates to that. Is, let's say there is a part of the system which is slow, and you are trying to improve the performance of that slow part. How much it's gonna impact the speed or the performance of the overall system? That's what Amdahl's law relates to. Like if we take care of the performance of the slowest part, how much it's gonna impact to the overall performance of the system. Okay. This law is often used in parallel computing to predict the theoretical speed up when the multiple processors are used. So basically, it all helps us understand what is the maximum theoretical performance gain we can get by improving a particular part of the system. So in this case, how much fast Hina can go, but no matter how fast she goes, how what is the limit of overall system performance Hina's moving faster can change. Let's understand, right? So Amdahl's law helps us how a particular part of the system is going to help in improving the performance of overall system, and this also allows us to allocate our resources, help us understand where we should be spending our resources to improve the performance. Okay, so let's look at Amdahl's law mathematically. It provides a simple way of calculating the performance gain that can be obtained by improving a particular element of the computer system. Okay, so what is the maximum performance gain? So what is the maximum speed up you can obtain by basically improving the performance of a particular part of the system? So speed of the maximum performance you can obtain. S is the performance gain factor of P after you implement the enhancement. So P is the part for which you are if improving the performance, and basically S is the performance gain factor of P after you implement the enhancements, and basically 1 minus P is the part for which you're improving the performance. 1 minus P is the part which is not impacted by it. So let's take an example. Okay, if a particular part can be improved by 30%, is, so let's say you have a part, okay, let's say in our case Hina, let's say that is 30% part of the overall system performance. Like it's a 30% part. Rest, if you change this, only 30% of the perform part of the system can be changed. And let's say you basically double the performance of it. Okay, so basically, which is S. So let's say there is a 30% part of the system and you double its performance. Okay, so in this case, the maximum speed gain which can be improved. So you basically you're only changing 30% part of the system, rest 70% part is not changing, and you are basically doubling the performance of the 30% part of the system. So maximum speed gain overall you can have is 1.18. So if a earlier system was working at 1, the speed gain basically you will be 1.818. So 1.18 times. So we see, right, 1 minus P is an important part of C, of the theoretical limit of performance benefit. If it's only gonna impact a small set, if P's performance is going to improve by only so much, by only if P is a very small percentage, you can't basically you will your theoretical limit will be very low. Okay. Now let us say rather than double, if you do 4, you will still hit a theoretical limit. Okay. So overall, if the parts one the parts for which you are improving the performance is a very small portion, you may not be able to get much gain, no matter even if you improve the speed by 10x. Okay. Now the second thing is, even if basically it's a one small part, if you should try to combine as many small parts so that your 1 minus p is better for overall performance improvement. So even if 1 minus p is half, there is the speed performance improvement cannot go beyond that, no matter how many processor you use, no matter how many percentage improvement, 10x, 20x you do. You will always hit a theoretical limit. And what is that theoretical limit? That's Amdahl's law helps us calculate. Now, let's consider using another example. Let's say you're going from London to New York, and let's say 50% of your time is spent on aeroplane. Rest is maybe check-in, maybe you're taking a bus or a car from home. So let's say your 50% of the time is on aeroplane. Now, if you improve the speed of the aeroplane, speed of the plane, it will have basically, maybe you improve the speed by 2x, maybe you improve speed by 4x, but there'll be a theoretical limit by which that can help improve the performance. Okay. So let's say you have the speed up of 2. Okay. Or even if there is plane journey time is reduced to 0, you will hit a theoretical limit. So let's say if we double the speed of the plane, the overall speed factor by which our journey time improves is 1.33. This is basically calculated by Amdahl's law. So if you double your speed, since it's only 50% of the 50% of the time consumed in your overall journey, the overall improvement of the system is only 1.33. Let's say we double the speed in again, even then, basically, even if you've done 4x, the speed up obtained is only 1.6. So basically, you are hitting a theoretical limit, which the theoretical limit eventually is basically 1 and 1 minus this p, which is basically the amount of system it impacts. Okay, so basically your speed limit improvement is gonna be, so this is 1 minus p. So your speed limit is going to be impacted by set performance p. So if you're basically p is 0.5, which is 50% of the system it's going to impact, maximum you can do is 2 times. Okay. So basically you're always going to be limited by amount of system a particular component consumed. So if we So the short summary of that is, if we focus on single optimization, we'll start seeing diminishing returns for investing on more hardware. So this then basically, after we have done some improvements, we should carefully reevaluate where to make enhancements after each optimization is applied. Okay, so you see, right, you have done this speed improvement from 2 to 4 here, 4 to 10 here, 10 to 100 here. Since the theoretical limit is 2, you have basically your returns, you have made 10x improvement here, but overall system improvement is not that much. You have started to see diminishing return. So this Amdahl's law also indicates to us that once we have done some optimization, we need to carefully reevaluate where to make further enhancements or investment after each optimization is applied, so that we have to make sure we are not hitting what is known as basically diminishing returns or the theoretical limit as per Amdahl's law. The other aspect in a computer architecture system is complexity. Okay, we normally want to seek simple and elegant solutions because complex solutions are difficult to verify, complex solutions are difficult to design, so it increases both design and verification cost, and it's also complex to difficult to imagine as well. So basically, in general, we complexity of the system, we want to keep it as simple as possible. We want to create simple and elegant solution, and we often want to understand how what the system which we have built and how we can predict the output and see then behave and verify it. So in engineering, right, simplicity is having simpler solution is always better and sometimes much better. This is basically a quote from Robert T. Caldwell from his book Pentium Chronicle. So in an engineering solution, we want to keep things simple, and there is also like keep it simple, stupid. Now, one of the ways to basically improve the overall system performance and which is very commonly used is making the common case fast. Whatever you're doing most of the times in a computer architecture system, try to make that fast. So making the common case fast will tend to enhance the performance better than optimizing the rare case. Because why that is the case? Because the P of that will be more because the common case is used more. How much it impacts system performance will be more. So making the common case fast which tends to enhance the performance better than optimizing the rare case. Ironically, the good part of that is, as in we want to reduce the complexity, we want to keep our system simpler. Often is the case that the simpler case is simple or the common case is simple and it's more often easier to pronounce. So that works in our favor. This common sense advice implies that you know what is the common case. Okay. And it is always not obvious what is the common case. So for that, you have to do careful experimentation and measurement and run multiple architectural experiments to understand that. So basically, let's take this example. Okay, so let's say you want to go place A to place B, but our most of common cases maximum they'll usually there'll be one passenger or two passenger in the car. So it's better to have a sports car which can sit two people, which is for the common case, than to make a minivan go much faster. And since our common case is like one or two people, it's better to make a sports car because that will allow our common case to go faster and overall improve the performance of transport. But and it's also ironically simpler to design a two people sports car than a minivan to go much faster than it usually can. So again, making the common case faster is an important concept, and it's basically sometimes not obvious to figure out what is our common case. So basically, experimentation, understanding the system, and measurement has to be done to figure out what is our common case. Now, what are the tools, techniques we have at our disposal to make the common case fast? We will be going into details of these at a little bit later, but at a high level, we'll understand what are the tools that we have at our disposal, that are disposable to us to make our common case faster. One is locality. Locality is basically it can be time-based locality, also known as temporal locality. That okay, I have done this operation. Now the next operation I am going to do this. It's basically very temporal locality or spatial locality. I have accessed a particular address, and basically next there is a high likelihood I will now address or access the next memory location. So these are exploited by your caches, your translation look-aside buffer, branch target predictors, etc. So we'll go into a little bit more details of these a little bit later. But right now, at a high level, we are trying to understand what are the how to make the common cases first. One is speculation. Speculation is we can speculate. Okay, this is now what the processor is going to do. So we may go ahead and do something before if it's needed or precisely the correct thing to do. The hope is that performing that operation early, we can improve our performance. Speculation is not same as prediction as it requires us to provide a mechanism to correct our guess if our guesses are wrong. Okay. Perhaps we have modified some state change and that needs to be corrected if we have speculated. Again, we'll go into a little bit more detail, but basically we are at a high level understanding what are the various case techniques we have at our disposal to make the making the common case fast. So locality, speculation, prediction. In order to for speculation to be profitable, we normally try to make the best prediction possible. There are multiple types of prediction, branch prediction, etc. Or in a packet on a chip network won't change direction. So we will make some predictions and try to make the performance faster. Then there is indirection, like virtual memory, reference something using a name or a reference in rather than the value itself. Then parallelism, pipelining, super skill processor, single instruction, multiple data operations, and graphical processing unit. Again, we'll go into details of that. Or specialization, like hardware accelerators, specialization, taking the common case and ensuring that is implemented efficiently in hardware. So take the common case, implement it really efficiently in the hardware with a minimum of superfluous logic, and that also allows us to make the common case faster. So we'll go into some more detail little bit later. At least couple of concepts we'll understand more. For example, one is locality. Principle of locality is that programs, and this is just a hypothesis, tends to reuse data instructions near to those which they have recently used. Now, basically, it can be temporal locality. Recently referenced item are likely to be referenced again in the new future, or a spatial locality, that items which are near have been accessed in memory. Nearby addresses tend to be referenced close together in time. Okay. So there is basically spatial and temporal locality. Like for example, reference LA elements in succession. You may have code where basically you can have this kind of for loop, and you are multiplying, adding the array elements. So that it gives basically you are referencing some in each iteration. This is temporal locality. You are basically accessing some say, different indexes of the array, that is spatial locality. So both spatial and temporal locality allows us to make the performance faster. Then there is speculation, which is basically doing something before you know it's needed. So right now, just at a high level, see, okay, these are the various methods. We'll go into details and how these are implemented a little bit later. And this is again mainly used to enhance performance. In a single processor context, there is branch prediction, data value prediction. You may do some prefetching. In multiprocessor context, there will be thread level speculation, transactional memory level speculation, some helper threads. We'll go into a little bit more details later in the course. Now we often use, now basically we have said, okay, one is Amdahl's law, which helps us understand a small part of the system, how much performance met the theoretical limit on the performance you can get from that. Then basically we talked about the concept is, as in whatever is the most common use case, should try to improve the performance on that, and what are the various tools and techniques we have to improve that performance. Now how do we make sure, as in we are improving the performance, right? So we have benchmarks to determine what are the common cases, and then that helps us guide the design process. Now basically the challenge is always to carefully evaluate these ideas quantitatively, because some